Hello, my name is Lorenzo Corrêa, and in this speech, I'll present results and discussion regarding the thermodynamic analysis of thermomagnetic motors. This work was developed by Luiz Lima and co-authors, supervised by the Professor Paulo Trevizoli at the Laboratory for Emerging Thermal Systems at the Federal University of Minas Gerais. The global energy demand is currently increasing. According to the World Energy Council, using more efficient energy conversion systems is a way to increase demand without increase the energy production. One means to do that is to recover heat waste through industrial process and convert it to a more useful type of energy, such as mechanical or electrical. The waste of heat can be divided according to its temperature. High grade corresponds to temperatures higher than 650 degrees, medium grade from 230 to 650, and low grade for temperatures lower than 230 degrees. However, recovering low grade heat waste is a low efficiency process, mostly made from solid state thermal energy harvesters. Among those, thermomagnetic motors and generators can be applied as thermal energy harvesters. In this figure, we can show how a thermomagnetic motor operates. In this case, we use the spring force to balance the magnetic force. Initially, in figure A, the magnetic material is placed in a low field region and it's cooled down by a cold fluid stream from the cold reservoir. When the magnetic material achieves a temperature lower than its Curie temperature, it reaches a ferromagnetic phase and the magnetic material is attracted to the high field region, as shown in figure B. The displacement of the magnetic material only happens if the magnetic force is higher than the spring elastic force. At this point, in figure C, the magnetic material is heated by a hot fluid stream from the hot reservoir, which could be supplied from a low-grade heat waste. And then, when the magnetic material achieves a temperature higher than its Curie temperature, and therefore a non-magnetic phase, and the magnetic force is lower than the spring elastic force, the magnetic material is moved back to the low field region as shown in figure D, restarting the cycle. This way, it's possible to convert heat into mechanical work. The motor can operate in accordance with different thermodynamic cycles, such as Ericsson and Brayton cycles. Let us observe the temperature entropy diagram of those cycles. First, we have the y-axis as the temperature and in the x-axis the entropy. Secondly, we can identify the isomagnetic field lines, the high magnetic field one and the low magnetic field one. Then, we can identify the Ericsson cycle, which is composed by two isofield processes and two isothermal processes. The isofield processes in the isofield processes, the magnetic material receives heat from a heat source or releases heat to a heat sink, while in the isothermal processes, the magnetic field changes and the magnetocaloric effect is observed. In this case, the magnetocaloric effect is quantified by the variation on the total entropy of the magnetic material. Finally, we can identify the Brayton cycle, which is composed by two isofield processes and two adiabatic processes. Again, in the isofield processes, the magnetic material receives heat from a heat source or releases it to a heat sink, while in the adiabatic processes, the magnetic field changes and the magnetocaloric effect is observed. In this case, the magnetocaloric effect is quantified by the adiabatic temperature change. In the literature, we can find similar results to the one presented here. Kishore and Priya studied the Ericsson cycle and evaluated different materials, including gadolinium. They made no evaluation regarding the demagnetization effects, and the evaluated results were regarding the specific work, the first and the second law efficiencies. As we can see in the results they presented, gadolinium was one of the materials which presented a higher specific work. And Bessa studied the Brayton cycle using gadolinium as magnetic material, and he performed discussions regarding the demagnetization effect, but he showed no results regarding that effect. He also evaluated results regarding the specific work, the first and the second law efficiencies. In this way, the main objective of the present research is to evaluate and compare the thermodynamic performance of a thermomagnetic motor operating according both to the Ericsson and Brayton cycles. In order to accomplish this objective, some considerations were made. So, the theoretical investigation is developed considering gadolinium as a magnetic material. Gadolinium properties were evaluated via the Weiss, Debye, and Sommerfeld theory, and thermodynamic analysis are based on the specific work, the first and the second laws of thermodynamic efficiencies. This figure presents the entropy temperature diagram for gadolinium for different applied magnetic fields ranging from 0 Teslas to 2 Teslas. This diagram was obtained using the Weiss-Debye-Sommerfeld theory, which can also be called as the mean field theory. Using this theory, we can calculate via analytical expressions the contributions for the magnetic lattice in the electronic entropies, and the sum of these three contributions results in this diagram. To evaluate all the metrics proposed in this work, initially we have to calculate the specific work, and it's calculated using the first law of thermodynamics. Thus, we have to calculate the values for heat input and heat output. To evaluate the heat input and heat output, a numerical procedure to calculate the areas under the entropy temperature diagram was used. This procedure was implemented in Python. Thus, setting the values for hot and cold temperatures in high and low magnetic fields, we can build the diagram and evaluate areas. Also, it's important to mention that demagnetizing factors were not included, demagnetizing losses. Hence, we can evaluate the areas for both cycles. For the Ericsson cycle, we have four areas. The heat input is the sum of all the four areas, while the heat output is the sum of areas A3 and A4. For the Brayton cycles, we have only two areas, and the heat input is the sum of both areas, and the heat output is just the area A2. Then, after we calculate the liquid work and the heat input, we can evaluate the first law efficiency and later the second law efficiency using these equations, where eta C is the current efficiency for a motor. These figures present the results for the Ericsson cycle. The x-axis is the hot reservoir temperature and the y-axis is the difference between the hot reservoir temperature and the cold reservoir temperature, also known as delta T. Figure A shows the results for heat input, Figure B shows the results for specific work, Figure C for first law efficiency, and Figure D for second law efficiency. Analyzing these figures, it can be observed that the maximum values for specific work are achieved over 300 Kelvin for the hot reservoir temperature and 60 Kelvin for the delta T. However, the heat inputs for these conditions are quite high, achieving values above 15,000 joules per kilogram, and thus the first law efficiency is small. The second law efficiency can reach over 30% as the delta T decreases. These figures present the results for the Brayton cycle. For the cycles, the results are in agreement with BESA, and they show that the specific work achieves the same maximum values for the same temperature and delta T, and again, the heat inputs are quite high in comparison to the Ericsson cycle. And the first law efficiency is small but a little higher than the Ericsson cycle, with maximum values of 0.8% at temperatures between 209 Kelvin and 320 Kelvin, and delta T under 40 Kelvin. And the second law efficiencies can reach 30% as the delta T decreases. Comparing both cycles, it can be observed that the specific work values are similar to both of them, with maximum values around 140 joules per kilogram. The first law efficiency is very low, and with maximum values around 1%, and the Ericsson cycle presented a more interesting result because at efficiency values around 1%, the specific work was 50 joules per kilogram, while it was 20 joules per kilogram in the Brayton cycle. This work presented a thermodynamic evaluation of thermomagnetic motors operating under the Ericsson and Brayton cycles. A theoretical model was developed combining the first and second laws of thermodynamics with numerical integration methods applied to the entropy temperature diagrams of gadolinium to calculate the amount of heat absorbed and rejected along a cycle. The proposed methodology was verified with previously reported results, and a good agreement was found. Thus, further comparison between the results for Ericsson and Brayton cycles were performed. The Ericsson cycle presented a more interesting performance. However, both first and second law efficiencies for the motor using gadolinium were quite low, and therefore it's possible to conclude that thermomagnetic motors are interesting when used to recover wasted heat only if the necessary power input to operate the motor, for instance the pumping power, is much smaller than the power produced by the motor. Future works will include different losses such as demagnetization losses in non-isothermal or non-adiabatic conditions. Also, different magnetocaloric materials will be studied following the same protocols. We would like to thank the Department of Mechanical Engineering from UFMG, especially though the Pró-Reitoria de Pesquisa, and CNPq for supporting this research with a PBIC scholarship. And here are the references used in this presentation. Thank you.